There's a lot to say about capacitors, but all I'm going to say for now is capacitors store electrical energy, and the amount of energy they're able to store is called their capacitance. What we're going to focus on here is the equations that determine the amount of capacitance you have when you connect capacitors in parallel and in series. Now, capacitance is measured in farads, but a farad is a lot of capacitance. What you're more likely to see are values such as microfarads, which is a millionth of a farad, or picofarads, which is a trillionth of a farad. In this video, we're going to be using nanofarads, which is a billionth of a farad. This eliminates a lot of zeros and makes the math and the measurement a lot simpler. The important thing is to use the same unit of measure throughout in order to make the equations work. Welcome to Scofflaw Laboratories. We're going to make a few connections, take some measurements, and do a little math. Let's start by looking at parallel capacitors. These are two capacitors in parallel, connected on either end. And the total capacitance is C1 plus C2 plus as many capacitors as you have in parallel. We'll put a couple randomly selected capacitors in here. We've got a modern polypropylene and an old mica cap. We'll find their values and plug them into this formula. Notice that they're not connected on the ends yet. We'll do that after we measure. And the first one is 4.683 nanofarads. And C2 comes in at 0.353 nanofarads. We have 4.683 and 0.353 as our values. We'll take these, plug them into this formula. C1 plus C2 add up to 5.036 nanofarads. Now let's connect them and take a measurement. Five nanofarads. We calculated 5.036 nanofarads and we measured 5 nanofarads. I'm calling that a win. Now we're going to look at series capacitors. And this is two capacitors in series. This time the total capacitance is the product of C1 and C2 divided by the sum of C1 and C2. We'll put the same two capacitors back in place. We know their values. We'll just plug them into this formula. 4.683 times 0.353 divided by 4.683 plus 0.353. So we'll take this equation and simplify the numerator and denominator. And we have 1.653099 divided by 5.036. And that comes out to an irrational number, so we'll use the first 5 significant digits. Total capacitance, 0.32825 nanofarads. Let's see what we measure. .337 nanofarads. We calculated 0.32825 nanofarads and we measured 0.337 nanofarads. That's within 3%. Look what happens when you have 3 or more series capacitors. Here's 3 capacitors in series. Now the total capacitance is 1 divided by 1 over C1 plus 1 over C2 plus 1 over C3 and as many capacitors as you have in the series. Let's put some capacitors in here. We have our 2 old friends. We know their values. And then this new kid on the block, this Mylar cap. We'll find its value. and to put all three into this formula. And C3 comes out to 220.6 nanofarads. We have our three values, and we put them into the formula. This is how you put a compound fraction into a TI-83 Plus calculator. It's all about the parentheses. 1 divided by parentheses, 1 divided by 4.683, close parentheses, plus parentheses, 1 divided by 0.353, close, plus parentheses, 1 divided by 220.6, close, enter. We solve this big compound fraction, and we'll round off the total capacitance to 0.3277 nanofarads. Let's take a measurement. Notice the probes are going to go on the ends of this series. And we come up with 0.339 nanofarads. We calculated 0.3277, and we measured 0.339. Still within 4%. There was an interesting trend in this experiment that we need to look at. When we had two capacitors in series, we calculated 0.3282 nanofarads, and then we added a much larger capacitor, 220.6 nanofarads. And when we calculated that, it came out slightly lower, 0.3277 nanofarads. And in both cases, the calculated value was lower than the lowest value capacitor in the series. The measured value of the 3 in series came out a little bit higher than the 2 in series, but overall the data at first glance seems a little counterintuitive. There is a lot to say about capacitors, and in future videos we'll examine some of their other properties. But the math worked out, and if you saw my video on parallel and series resistors, the equations should look familiar. So grab a handful of parts, make some connections, take a few measurements, do a little math, and see for yourself, because this is the best way to learn these principles. And then come back to Scofflaw Laboratories for some more electronic basics.